All right, anyways. All right, guys, let's go ahead and get started. I told y'all today we'd be going over the basically the hardest assignment, so here it is. Nice, I like it. So it's going to be these 5 cards right here. Originally, all these 5 cards were one document. I tried to break it up for you in order to help you out. The point of this is that we're going to implement our single cycle processor. So let's see if I can load up the lecture for that, just so it's very clear what I'm talking about. Good morning. How's it going? Open that up, and there it is. Okay, we're going to implement this, but inside of Verilog. We have, hopefully y'all have created all the pieces for it, and y'all are going to present all the pieces for it next week on Tuesday, right?
Sure.
I see what you did there. You pulled out another desk, so it wouldn't have to be the 3 amigos. All right. So I tried to break this up for you. The first one is to get halt working. And before I move that to the wrong swim lane, let's move it down here. So first one is get halt working. The idea for this one is you want to put together a processor to where it's simply you get the halt instruction loaded. So you're going to create a program. The whole program just says halt. It loads that program in. It begins execution and then sees the halt instruction and gets out. That is all you want to be able to do here. Nothing else. This actually will take a little time to set up everything, because you're going to have to set up your test bench of your processor, as well as creating the processor, which has everything inside of it. So this one will take a little time, but it shouldn't take too long. Keep in mind that to stop your simulation, you want to call the finish function. By the way, real processors really don't have a halt instruction, because that doesn't make any sense. You just want your CPU to turn off. If you want that to happen, you turn off the power, not tell the CPU to turn off. Yeah, that doesn't make any sense. But for our simulations, it's very helpful to have a halt instruction so we know when we want to end the simulation. So we need to create an assembler with the halt instruction and get out. Of course, that also implies we need to have an assembler. Well, I have written an assembler for you. Wasn't that nice of me?
That was. It is.
So if you go into the repository on your single cycle processor, you'll see an a.c. That is the assembler. And I went ahead and gave you a loop example.asm. Oh, you can't see that because of the projector. Good morning.
Good morning, right?
If you type in make, it'll compile the assembler into basically.
We still can't see it. Right?
Who does this?
You know, if all the lights were off.
Yeah.
It would be a heat.
He's got to make the wall change.
I don't think this is a shame. Visibility.
Shame.
Is that better?
Yes.
Yeah. Actually, a lot better, to be honest.
It's way easier to see now.
Okay. So for those online, I turned the lights off. Woo! All right. So it compiles the assembler into an ASM binary. Good morning. Then it calls the assembler on loop example.asm, and the output it's called loop example.machinecode. And it does actually print out the output for you just to be helpful. But let's go ahead and first look at the loop example.asm. This is the assembly for it. Now this assembly is assembly that's specifically for our LC Little Computer 64-bit processor. It is not x86 verbatim. I was not able to get it to match x86 because there's a couple of little nuances I wasn't quite able to get correct. So keep in mind this is a little different, and we'll go through this in a bit. But right now, just notice that this assembly, it at least looks similar to x86. You see some move, in your instructions, you have a label, etc. Notice that in here, the labels do not have a semicolon afterwards. And it's also noticed that the instructions are not the first thing. So one thing to keep in mind when you're writing your program is you need to space out and then begin your instruction for this type of assembler. Okay. Now, if you look at the machine code, this is a bunch of, hex values. This is perfect for read mem h, which is what you can use inside of your Verilog simulation in order to read this data to both your data memory and your instruction memory. So make sure both of them get this data when you begin simulation. Now, this is the read mem h for the loop example.asm. Obviously, you're allowed to write other programs. You probably want to write a halt one. For example, let's do a halt one real quick. Notice I tab out and hit halt, and then I'll go ahead and ASM, halt.asm, and halt.machinecode. And then I can go look at halt.machinecode, and it just has the halt instruction. Again, let me show you what halt.asm looked like. Very important, I tabbed out. The halt was not the first instruction, because the thing in the first column is your label for this assembly. All right. So we'll talk a little bit about the assembler. You can compile it and run it. Hopefully it will work for you. It should work. I've tested it. But keep in mind that this is the first class that's using the new type of assembly. So definitely give yourself some good checks. But if things are really looking weird, please send me an email. I know how these things go the first time you make a transition from what you've been doing that's running perfectly to something different. Oh well. All right, so I think that takes care of that. This is 5 points because this is going to take you a little while to set this all up. It is not that simple. But luckily, the nice thing about the halt instruction is, let's see if we can go back to our data path, is for halt, what part of the processor do we need to have working in order to get halt to work? Ooh, I'm asking y'all. This is to help y'all out. The what?
Any of them?
I'm sorry, I didn't hear you.
Any of them?
Any of them? Do you need everything here in order to get halt working? Do you need to be able to access data memory in order to get halt working? It doesn't interface with data memory. So obviously we don't need data memory. So the question is, what part of it do we need in order to get halt working? So this is important to think about because it'll help you build together your processor. Also, it's very important to think of this as what is the minimum amount of work I can do in order to accomplish the task. That is going to actually help you immensely on this project. Don't try and engineer the whole thing out at once. You will be really sad. Try to do the minimum capable in order to get a simple program working first and get that working before you get other things working. So what is the minimal viable product? Ooh, that is actually a software engineering term. Minimal viable product, the minimal program or the minimal number of components needed in here in order to get halt working. Right, okay, because the halt instruction side instruction memory. Okay, so we need instruction memory. That's right.
PC as well?
We need the program counter. Sure do. What else? Actually, is there anything else?
No.
No, because the program counter, you set it to 0, you read from instruction memory, it gives you halt, you exit. Everyone got this? For the halt instruction, you literally want to set up your implementation, load everything into instruction memory, let program counter just be 0, go into instruction memory, get the halt instruction, get out. That's all you need to do. All right? Don't try and do anything more. You're going to be sad.
I'm already sad.
You're already sad. Excellent. I mean, good morning. All right. So that was instruction memory. Now, that's why, so it's 5 points, but you only need really 2 components hooked up correctly in order to make this work. But in order, the trick to this is you need those 2 components wrapped inside of a single cycle processor and then a test bench around that. By the way, your test bench should only pass a clock and reset to your single cycle CPU. There should be nothing else passed in. Your single cycle CPU should take care of everything else besides the clock and reset. All right. Now, any other questions about halt? Nothing? Alrighty then. So that's 5 points. And we'll take, oh, we already put that over there. Get halt working. Next comes load word. This is going to be the hardest one. But unfortunately, there's not much else you can do. I'm going to go ahead and change this to move L. Let me put it this way. It's called move L / load word. I'm giving you the different names because these are the different names that are going to be given for this one instruction. I called it load word is the easiest way to think of it in my opinion, because you're loading a word of data from data memory onto your processor. Woo! Let's go jump over and look at the code at least of what that may look like. So loop example. So this is the move L instruction. It's the top one because we're moving from 0 plus 5, namely down here, or moving 5. Knows that 5 maps to here, so we're moving the value 5 into register 1. What is this 0 thing? Well, the 0 is the base, and that's register 0. Hey, look, register 0 is always 0. So you're taking 0, adding to what the address of 5 is. Notice that this is a symbolic address, so it knows to go down to 5, get the address of this thing, and shove that value in for 4 bytes. So, and then take that value and put it into move. So it's going to first calculate the address, 0 plus wherever 5 is, and then the solid brackets mean go to that data memory and grab it, and then put the value there inside of this register 1. I kept it as move because that's the way it's done inside of x86. I just realized this is hard to see. That's not too bad. But you can think of it as move load or load word, whichever one is most helpful for you. So the question now is, what parts of the processor do you need working in order to get move L working? Now, before we begin, in order to have a test case with move L, you're going to have move load word and halt inside your instruction, which means now your program counter needs to increment. So the next thing you also need to get load word working is you need to have PC, go to PC plus 1, and then go back to the PC. Notice you don't need the mux yet because we haven't implemented branching. So you only need to have PC equals PC plus 1 because we're not doing a branch or any type of jump. So again, do the minimal necessary in order to get what you need done, otherwise you're going to go insane. So get it to do PC equals PC plus 1. That's going to be your first step. So the first time you write your program, do a load word, next instruction is halt, and make sure that it can actually halt. That'll be your first test for getting first part for learning load word. Then after that, what do we need in order to get load word to work? We're reading from, yes, loud and proud.
Data memory?
Yes. So we need the
ALU?
We do need the ALU. What's the ALU going to do? You got this, Perry.
No, that was all. That was my
That's
favorite.
all.
That was
All right,
best.
someone help Perry out.
Can it access the data memory?
Right. Right. But what is the ALU producing for the data memory? What does the ALU do? Arithmetic logic unit. It does.
Arithmetic.
Oh, nice. What arithmetic do we see in the load word?
Adding.
An add. Okay. Not trying to.
I said addition, that's my fault.
Oh, Perry, you gotta be loud and proud.
I know.
Amber is louder than you.
That's fine. I'm unsure.
That was nothing
you know?
against Amber.
I'm a loud person, so I don't
No, you're
support
not.
it. I'm not.
You
Well, I mean,
can
when
be.
it comes to, I second guess myself, you know?
Yeah, you gotta stop doing that.
ALU.
Oh, nice.
Got it, alright.
So we need the ALU to get the address. Where's the address of the ALU going to?
It's going to data memory.
Data memory, so we need the data memory as well. What part of the data memory do we need working for the load word?
All of it.
So we need both reading and writing? We just need read. So we just need the read part of the data memory. Of course, we need the enable line working as well. All right, where does the data memory go back to? The register file. We could mess with this mux, but we don't need to at this moment, so we'll just send it back to the register file, which means we also need the register file in order to get this one working. Yeah, this is why this one's hard, is because you're going to get a lot of your processor implemented in order to just get this one instruction working. All right, so you got to get the register file. You got to get the ALU working. You got to get the data memory working. What else needs to be working?
Instruction memory.
Correct, but we got that working from halt, right?
Awesome.
Nice. What else are we missing that's staring you at the in the face at the very bottom?
Control ROM.
Right, because we actually need to send the proper signals. What's that?
I said 6x64 decoder.
With the control ROM. So, on top of, so let me go and recap real quick. As a recommendation, again, you don't have to do it this way. You're free to do it whatever way you want, but this is the way I recommend it. When you had the halt instruction working, you just had P program counter instruction memory. That's it. To get load word and halt working, you got to do PC equals PC plus 1. Don't worry about that mux. Just send it right back in. And notice that this has to be clocked, so make sure you still have your clock working. That PC only updates on the positive edge of clock. Instruction memory feeds it out. Notice you need to fan it out correctly to the register file, which would read the two values. We don't need this mux right now, so just send it to the, well actually, we send it to the register file, and we have to do a sign extend, because I forgot about that one. This is a number. Oh boy. So it goes to register file, goes to sign extend, just forward those two values to the ALU, which does the addition. Go to data memory, which should be enabled, and read, which should be coming from your control ROM. Send that back to the register file, which should write, and it should write whichever one of these is important. I'll let you go and investigate which part of that is. And then that's all. By the way, I highly recommend at this point you have a mechanism to print out the contents of your register file every cycle. That way you can see what has changed every cycle. Because one, it'll help you test, and two, if you don't print out the components of your register file, you will fail because I will have no way in order to test your implementation. All right. So, hopefully you can see that that is a good portion of your processor, which is why the load word is 13 points. And you'll have very few other 13-point cards. But this one is going to be the big one. Even though all it says is implement the load word instruction. Because that's all you got to do. All right. Next comes add. Oh, we don't want to do nor. Add and no up. Okay, so what do we need to do in order to implement and on top of halt and load word? Well, I'll answer this one for you because it is a little hard to see. Load word has register file the ALU. We need to implement this mux first because the add creates the second parameter here. So you need a mux to select between the sign extend and the one coming out here. So implement that and make sure your load word is still working properly from your previous test case. The other thing we're going to need to implement is the ALU normally sends it back to this mux. The load word is this line, so we need to add this mux as well and control it based on which instruction it is. So implement this mux and make sure it still works with load word. And we also have to implement this mux, because which of these bits go forward to the register file for writing changes based on the load word or the add. So really, the three things you got to implement are that mux, and that mux in order to add on top of load word and halt. And, by the way, is the same thing. We just send a different signal to the ALU. And no op, well, you just don't do anything. You just disable these two lines and you're done. So hopefully you can see that doing these three together really makes some sense, because you really just need, once you implement these three muxes, you're done with those three instructions. I mean, you do have to set up the enable lines for each one, but that's pretty minor compared to the muxes, and definitely pretty minor compared to what you just had to do for load word. So, load word, and the reason you have to do load word first is in order to test add, you actually have to put data inside your register file first so you can do something. So that's really why you need load word before you can test your other instructions. So again, once you get load word done, go ahead and implement add and no op, put them inside of a program, run some tests, make sure the output makes sense, and you should be good to go. Any questions on those three? Yes.
Are those 64-bit muxes?
Yes. Well, no, I'm sorry, hold on.
Those are 5-bit muxes.
These two are the 5-bit muxes. I'm sorry, this one's a 5-bit mux because it's selecting between what register to write to. This is 64 bits because it's 64-bit inputs. One coming from the sign extend, the other coming from the register file. This is 64 because one's coming from the output of the ALU and the other's coming from the output of data memory. Warning, you're actually going to need a sign extend data memory. I didn't write that up there because it's 32 bits coming out of it. Who does this? Oh, I do. All right. All right, so and that's 8 points because it does take a little time to get those muxes, and you have to test load word and make sure you didn't mess up a load word, which can be tricky. All right, hopefully you can see store word makes it's a good one to go next. The reason is because next the only two instructions you have left are store word, aka move in the other direction, and branch of equal, or actually in this case it's CMP and jump, but we'll get to that in a moment. So let me go up and make sure I label this correctly, because this is the old version. And that is when you take the address right here and move it, and I'm sorry. Woo. Excuse me, this is not the one I'm looking for. But this will work. So you load register reg2 with -1. This is in backwards. So let me find another store word. I don't have a store word here. I will need to present you a store word because I didn't write one in here. Sorry, guys. But with the store word, you go back to the instructions. By the way, what's the format of the store word? Let me go show you. Is it in here? Where is it? It's in the other one. So let's go take a look at that. LibreOffice, materials, PowerPoint, lectures, PowerPoint, there we go. And that one should be in, where was it? Was it 01? Huh. I thought I had it in 07, but I didn't. It's on that one. It's on that one. Wait, no, it might be in this. No, it's on that one. Nope. No. It's not on this one either. Okay, guys, where to go?
You don't.
Who deleted it? Did you delete it? Who's been messing with my slides?
Probably that golfer guy.
It was totally me.
They're gone for good.
I don't know exactly.
I remember presenting them this semester too. That's what's funny. Wow. Where did it go? Because that's the architecture.
Good stuff.
So we are looking for R type. Oh, it's 07 assembly introduction. Interesting. Okay. That is not it at all. Nope, that's not it.
Yeah, I deleted it.
You deleted it? Who deleted it? Why is it not in here?
There was an I. Your third hand.
Wow.
Oh no.
Yeah, this is.
Paul the West couldn't take it anymore.
Paul West just could not handle it anymore.
He said,
Yeah, because if y'all don't see the instruction format, this does not make any sense. There it is. It is in here.
oh man.
There we go. Wow. Ooh, that took a long time. Okay, so it's in the same slides.
Bless you.
You're not blessed.
First.
So there's the I type. Perfect. So R type, when you want to do add, and, or CMP, notice that the opcode, the first 5 bits here, the destination, the target, and then well, those are unused. And the I type, you have that offset, which is encoded. So move RS, that's where you're moving RS equals memory. And this is move to save. This will actually save it out to memory. That implies that my example is backwards. Huh. I'll have to fix that. All right. Oh, it is.
Oh no.
The slide is right. The assembly file is wrong. So someone will remind me to fix the assembly file. Because apparently
Fix the
that's an
assembly
old
file.
version.
When's a good time to remind you?
Oh, right after class.
Gotcha. What a reminder.
Right, so this is the load word. This is the store word. Notice that you're storing memory from RS plus offset equal to RT. So that's the store word. Good. That's the instruction you're implementing right here. Whew. Thought for a moment this was gone. That would have been real bad. All right. What do we need in order to get that working? Oh, good. It's right before the data pack. It was right before that the whole time. Duh. Okay. So to get store word working, well, you still have that whole address calculation right here, which is good. That's great. But you need to forward from the register file the value and then enable and write. So in this mode, you're going to enable writing for the register file, and then you're going to make sure you forward from the register file to the data memory. And that's actually about it. Naturally, when you do this, just make sure all your other instructions still work. The reason I keep saying that is make sure you have a repository of the test cases to ensure everything's still working properly. Because trust me, once you add another instruction, chances are you're going to break something else. That's how life is. I also highly recommend that once you get it working, commit it to GitHub. That way, if everything fails, the world explodes. And by the world explode, I mean your computer explodes. At least you'll be able to check out a correctly working copy of this processor. All right. Ooh, that was bad. Okay, and so we got that one. And the last one, it used to be called BEQ because there was one instruction, but since we're doing x86, it's now called CMP/jump address. And now I need to copy and replace BEQ with this everywhere I see it. All right. So, remember this one where things get a little tricky? So, CMP, when it comes in, the ALU needs to compare the two and set an internal compare flag equal to 0 or 1 based on if the two are actually equal. Then if you're doing a branch, now you have to add this circuit of doing PC plus 1 plus sign extend all the way back over to that mux. And then if you recall, we had this one picture. Let's run right over. Or let's not. Where was it? Oh, it's in here. There it is. Whew. Where if the instruction is a jump address, only do it if the previous CMP flag was true. Then you would take the second line. Otherwise, in this example, it was 0, so you take the first line. And then that's what you need to add for the BEQ. This one does take a little more time because there's a couple more components you have to hook up. And namely, you also have to get this mux working correctly up front, which has, for some reason, caused lots of issues for students. Go figure. I don't know. I'm just working with it. But then after that, your single cycle processor should be working. Any questions? Comments? Screams? Ah! I was actually expecting a really bad scream for this one.
Defines a bad screen.
Like blood-curdling terror?
Yeah, there's something bad.
What's that?
We gotta listen to
So like it hurts your ears level of that.
Yeah, exactly. You got it. You got it. That's what I was expecting. Yes.
I know I asked about the monks, going back to the mux. To test it, there was some sort of like command that you could give the line so that way you wouldn't have to type out every single command. You could actually have it loop and it would just input things a certain way. Can that be done when you actually implement the module as well, beyond just testing?
I mean,
You actually
sure.
have to go through and like code out 240 lines to get it.
I mean, yeah. If there's a generate, if you want to use the generate functionality, sure.
Generate.
But I don't think it's. I mean, for this, I don't think it's going to be that helpful. It will be helpful for implementing your muxes, but for this,
Yeah, I'm talking about the muxes.
Oh, okay. Oh, the muxes. Yeah, yeah. There's a generate function that'll help you out. Any other questions, comments? Nothing. All right. So you got this.
Of course we do.
This is the hardest assignment. Just FYI. After you get this one done, things get a little. I don't want to say easier, so much as.
Less difficult.
Less bullcrap.
What? This is all applicable knowledge.
Please explain how that terminology works on this. I can't wait to hear this. Oh, please. Oh, please
I
tell
spent like 5
me.
hours yesterday typing out the same things over and over again.
Mm-hmm.
So I'm a little off.
Mm-hmm.
So to me, this is nonsense.
Mm-hmm.
Why are there so many things we have to type out the same? Why does everything have to be 64-bit? That just seems like...
Yeah, why is that?
Why is that?
Why is that?
Because I was directed to do x86 64.
Who told you to do that?
Let's see, sessions and len.
The national
They are the worst
accreditation
right now.
committee.
The national what?
Accreditation committee. I don't know. Whoever says CSU is a national accreditation.
By the way, Brian, if you don't want to type it all out, which I don't blame you, you could write a script that generates the Verilog code for you and then dump that to a Verilog
How
file.
do I do that?
You write a script. Did you take scripting?
I can't remember how to do that.
Oh, well, then I think we know whose fault this is.
My memory, I guess.
What's that?
Whoever taught him script.
Which wasn't me. Nice blame shifting there. Nice blame shift. Do you notice how it went to me? I bounced it back, and then you took it from him and moved it to a third party. And
Yeah,
since now that
Amber.
now that the third party isn't here, they can't defend themselves. Well
I'll
done,
have to
Amber.
blame
Well
Big
done.
Brother.
Well done. Good work. Any other questions?
What day is day
24.
Thank you, Blake.
I'm gonna forget that one.
Spring break.
I gotta change.
It's after spring
It
break.
starts.
That's what I meant. Post spring break.
Post, I didn't hear post, sorry. I just heard spring break. I was like, no, it's after spring break. Although making you do spring break is
No.
tempting.
It was during
spring
break.
No, it wasn't.
I
It
will
was
kill
the
you.
week after spring break.
No, let's do the 17th, and then we move to
Yes,
the 24th.
and our
Yes.
spring break is 9th through the 13th.
Yes,
Yes.
that's true. That's
It's the 24th.
Let's keep it.
But now it's the
It's
24th. Because I'm not evil, I'm just demanding. There's a difference.
How many more assignments do we have for this game? Just around like a ballpark. Like how many unassigned stuff?
That's a great question.
I'd like to know what I'm having to prepare for.
Well, these are all your questions that are left. You can look at all the questions for the rest of this course, by the way. It's kind of funny, including your midterm and your final.
Why,
Wait, we have a midterm?
Yeah.
Yes. I mean, hold on, let me rephrase that. Yes.
Is there a test I need to be studying for?
No. Yes?
For
Yes,
this
but
class?
actually no.
Yeah.
Actually, I can answer that. No, not at all.
Okay, that's all I need to know.
Your midterm is take home.
It's cards right there.
It's just it's right there. You can start working on it right now if you want to.
Oh, yes, I will.
Will those be due alongside gate 2 though?
No, no,
Oh.
no. Unless you want them to.
No.
No, but I'm curious when it'll be, when we'll do
No. For the
it, as
love of
compared to the
everything
rest
that is
of
unholy,
guys.
no.
I'm more, wanting to know when we'll do them, like.
Actually, some of these need to be due. Well, no, they don't. We're gonna have to have gate 3 is gonna have to be broken up into two parts.
Okay.
Yeah,
We should change it on Scrum to have gate 3A and gate 3B.
Yes. Or maybe we could jump to the other Kanban board and not use Scrum Do anymore.
Do you really want to set that up that late in the semester?
Do you want to use me more?
Yes.
How many of y'all like Scrum Do?
Well, no,
It's
no,
not-
they're
it's
not.
not-
Are you kidding?
Wait, what's the other?
Is that even a question?
Worse.
Oh, I haven't showed you what the other one looks like?
No, you
No.
haven't.
Oh,
As far as I
it's
know.
not pretty, but it just works.
It's
Does
just
it not delete
So,
cards?
does it
That's
take
correct.
you-
It does not delete cards.
Does
It's
it
already
take
got
you
a
Excel
big plus.
documents without, giving you a bunch of, lumped together garbage?
So frustrating.
You can imagine.
So it's not pretty, but it I mean, it's the same idea. Let me go back one. So you still have your swim lanes, you have your cards. The nice thing about this one is I can control it so you don't actually put it into graded and whatnot. Yes, Trevor?
Sorry, I was
No.
laughing at something else.
You
Does it
sure?
also,
Yes, 100% was.
my question was, does it take, XLS documents and not explode into like a.
Oh, so
giant-
what's beautiful about this one is when you click on a card, you can go over and scroll down to, what is it called? Duplicate to another project. And then you duplicate it to your project and it copies it directly there without you having to mess with any XLS
So
document.
instead of us having to download XLS documents and then import them in, we would instead just duplicate to another project from the computer architecture
Mhm.
workspace and then just copy
Mhm.
it over to ours.
Mhm.
Neat. Yeah, that would work better.
Why are we not using this? Because I didn't discover this until a week before classes started.
Well, I mean, like, why are we not using it now? Like, I understand, like, you just set it up
Oh,
on that.
so there's that, and there's something like time, I have kids. Yeah, it's always the kids, it's always those kids. Because I love those kids.
You know what will happen to Scrum Do when our grace period ends?
It disappears.
Because our grace period is like the day that finals stuff is due. And
Yeah, so don't mess up.
And so what happens if you
It's
haven't
kinda harder
gotten
to
around to
read
grading
your
everything
stuff.
and everything just disappears?
We get hundreds.
Well, I'm going to record your grade before then. You're going to have all your oh, I know. Here's a good answer. So what's probably a better way to do this is at least have the final go through this. That way all your grade cards and Scrum Do are done before the grace period. And then you can do the final over here, and then we can do a quick little, how was this? Okay. Well, that